Here is a surface area problem where we have to find the intersection of two cylinders, the surface area that results in the intersection of two cylinders. And in this particular problem, our cylinders are y squared plus z squared is equal to 1. So that's going along the YZ plane. Let's see. So in the YZ, there's a circle, and then we make a cylinder out of that. And then you have x squared plus z squared is equal to 1. So along the xz axis, you get another circle, and it goes this way. And so you kind of see that the intersection looks kind of confusing from the drawing, but if you look at the intersection here, you kind of see different parts of this. You have one cylinder, the cylinder that's like beige or yellow color, has this part on the side and then another part on the other side, and the cylinder here in the blue color has also these sides. Now at Washington DC, I took a trip there some years ago, and I was in a subway system, and here is how the intersection would look like. You see these lines that cross over here. That's kind of like these lines that cross over here on the top, and then so cylinders going like meeting in a perpendicular angle. Just so we can get another look, let's take a look at it in CalcPlot 3D. Here are the two cylinders that we're talking about. We have two cylinders that intersect at this space. Now, if I look at it just through one tunnel, I see a circle. That's like the XY, or that would be the YZ plane shadow. And what we can do is we can take away the cylinders and see that this is what's left. And if we look at it from the other side as well, this is the other side of the cylinder, and then the yellow would be the other cylinder. Alright, so that's the figure. I think it's hard enough to try to imagine. I encourage you to try to make it with Play-Doh or something. But what we're going to do is we're going to integrate, and so they look like there's going to be 4 sides to this, and what we're going to do is we're going to focus on one of them. It doesn't matter which one, but let's just randomly select this one. This looks like it's coming from the cylinder, it's coming from the cylinder X, I would probably say it's coming from the cylinder x squared plus z squared is equal to 1, going along the y. And it's being cut off by the cylinder y squared plus z squared is equal to 1. And so we're going to see this image from the top view. By top, I mean going directly from the x-axis view. Okay, so let's select this. Let's see if we could take a picture of it this way, and so that we can label it in our notes. So we got a few pictures of this, but let's take a look at this picture and see if we can annotate it. All right. So just to be clear, this surface here, this surface in the blue, is coming from the cylinder going along the y-axis. So that's x squared plus z squared is equal to 1. And since we're looking at it from the positive x-axis, I would say this is from the positive square root of 1 minus z squared. So that's the surface. And then your domain is looking at the YZ plane, and that's that circle of radius 1. So if we look at it, the circle of radius 1 on the YZ plane, that's going to be your domain. That's where you're going to integrate over. So this is our function. Let's call it f of yz, because this is an x equals function. And notice there's no y in it, but that's okay, because it is a cylinder going along the y-axis. And then our y limits is going to be, or the yz limits would be these limits. So initially, well, let's see, we're going to, using the formula for the surface area, we're going to change the variables a little bit, because we're going to shift our point of view to integrate over the YZ plane. So we're going to want f sub y. So the derivative of this function with respect to y, since there is no y, is going to be 0. And then f sub z, the derivative of this is going to be, well, it's going to be 1/2 1 minus z squared to the negative 1/2 times negative 2z. And then I suppose we can simplify this to whatever we want to or need to. The 2's would cancel. You'll have a negative z in the numerator, and then 1 minus z squared to the 1/2. So let's just put a square root there. So that's fz. And then our domain here is going to be a circle, radius 1, and the YZ plane. Alright, now we can jump directly to polar coordinates, which is the most appropriate thing to do, but let's just write this out for a minute. So our surface area is going to be a double integral over this domain here that we're calling D. And then we have the square root of 0 squared plus, now we have a negative z over 1 minus z squared to the 1/2 power squared plus 1. That 1 comes from the formula. And then we'll call it dA, but dA is actually going to be dy dz instead of dx dy. Now before we turn this to polar coordinates, let's see if we can simplify this inside here of the square root. So inside of the square root, we're going to see z squared, and then we have a 1 minus z squared. 1/2 squared is just going to be that itself, plus 1. So let's find the common denominators, which is 1 minus z squared. So I have a z squared plus 1 minus z squared, so the z squared and the z squareds cancel. I just have a 1 divided by 1 minus z squared. And so that goes under a square root. So then we can rewrite our double integral over d, the square root of 1 over 1 minus z squared dA, or dy dz. Okay. So this is, by the way, this is just a surface area of one side of this out of the 4 sides that we're looking for. So if we want the total surface area, let's not forget to multiply everything by 4. So let's do that here. Multiply it by 4. All right. So now let's change it to polar coordinates. I don't think that's gonna, I think that would be the appropriate coordinate system, because trying to find the limits of integration in using circles might be a little tough. But in polar coordinates, let's say y is equal to r cosine theta, and z is equal to r sine theta. So it's the same rules, except the y and z are switched, or we're used to looking at x and y, but it doesn't matter. So your radial distance is still going to go from 0 to 1 as if you were looking at the circle on the xy plane, and then your theta goes from 0 to 2 pi. So these are still going to be your limits. So we're going to change your limits. So we have a 4, a double integral, and let's not forget to change. I'm going to simplify this a little bit. The square root of 1 is 1, so let's just leave that on top. And then we'll use the z, which is going to be r sine theta, and then we want to square that, so it's r squared sine squared. And then the dA in polar coordinates becomes r dr d theta. So our r goes from 0 to 1, 0 to 1, and then our theta goes from 0 to 2 pi. Unfortunately, it doesn't look like there's going to be any easy ways to integrate this. We would have to use some sort of trig substitution with respect to theta, and then we're going to have to use some a u substitution would work with r. So actually, this is probably doable by hand, but I'm going to skip over that and go ahead and use Wolfram Alpha. So let's use Wolfram Alpha. Okay, so let's integrate. This is going to be the integral, and the first integral is going to be with respect to theta, and then the inner integral is going to be with respect to r, and the integrand is 1 divided by 1 minus, and let's put a parentheses, and r times cosine, or was it sine theta. And so this whole thing was being squared, and this whole thing was in a denominator. So that's our integrand. Oh, and then we have to multiply by r. Let's just change this 1 into the r. Or, you know what, just so that we can avoid confusion, since we can just over parenthesize here, let's multiply by r at the end so we can see it. And so the r is going to go from 0 to 1, and then our theta limits are going to go from 0 to 2 pi. Okay, so let's hope this Wolfram Alpha will be able to read this properly. And it looks like it's this one. They simplified it to r, and then it looks like that's just going to be equal to 2 pi. We don't have the 4 out there yet, but we'll just multiply everything by 4. So I think that's it. And multiply this by 4, and then multiply this by 4, and then multiply this by 4. So it looks like it's going to be 8 pi. So the surface area looks like it's going to be 8 pi. So one of these areas is going to be 2 pi, and then there's 4 of them, and then that makes 8 pi. Okay? So that is the surface area of this cylinder, or these two cylinders intersecting, and then the result are these 4 pieces of the cylinder that come up here, and then they are each equal to, the surface area is each equal to 2 pi, and so the whole thing's equal to 4 pi, or 8 pi. Alright, hope that helps.